Alright, so if you remember in my previous calculation, so I actually replaced that whenever I come across cosine pi in my calculation. So I replaced that by negative 1 to the power of n. So this is actually something that you can use to simplify your calculation. So when you do Fourier series calculation, you come across sine n pi, you can actually substitute that as a value of 0. And cosine pi is going to be negative 1 to the power of n. So why is that so? Because of this. Alright, so n, if you remember our series, it starts from n equal 1 to infinity. It's actually natural numbers, counting numbers, 1, 2, 3, 4, 5, 6, 7, and so on. So when I have n equal 1, so sine of 1 pi, if you use your calculator for this, remember to change that to radian unit first, that is going to equal 0. Or even if you have sine of 2 pi, so that is going to equal 0 as well. Sine of 3 pi is equal 0, and sine of 4 pi is also going to equal 0. And even if you have sine of 100 pi, it is still going to equal 0 as long as n is a natural number, counting numbers. Okay, so that is why when you come across sine n pi in your calculation, so simply substitute that by 0, and automatically your calculation will be simpler. Okay, another trick is that when you come across cos n pi, so if you have cos of 1 pi, so this is going to give you negative 1. So if you have cos of 2 pi, it's going to give you positive of 1. So cos of 3 pi is again negative of 1, and cos of 4 pi is going to be positive of 1, and so on. It's going to alternate. But I want you to notice the fact that when you have an even number, so it's going to be if you have an odd number, so the value is going to be negative 1, and if you have even number, so the value is going to be positive of 1. So which is what happened over here, negative 1 to the power of n. So that is why when you come across cos n pi, simply replace that by negative 1 to the power of n. So now let's have a look at the second example. So I bring it up to another level. Previously we only have a function of a constant, so now we're going to start playing with a more complicated function. So I have a predict function, so defined as f of t equal negative 1 minus t from negative 1 to 0, 1 minus t from 0 until 1, and from here we know that the period value, that is going to equal 2. So first we're going to sketch the graph in the interval from negative 3 to 3 in order to identify whether it's even, odd, or neither. And then of course we're going to find the Fourier series. So now let's start with A. So here I'm going to prepare the axis first. So I know that the interval is bound to be from negative 3 until 3. So 1, 2, and 3 on this side. Another 1, 2, and 3. Right, so this is going to be my function f of t, and this is my t-axis. So 1, 2, and 3, negative 1, negative 2, negative 3. Okay. So in order to know what is going to be like the value that I need on the f of t axis, I need the coordinate first. And of course, remember what I did before when I discussed with you 4.1 on how to sketch for predict function. So we choose the lowest and the highest value of t in order to find the graph of negative 1 minus t. So when t is equal negative 1, so I'm going to substitute right here. This value of t equal negative 1, I will get negative 1 minus negative of 1. So that is negative 1 plus 1. I will get a 0. And when t is equal 0, so I will get that my f of t is going to equal negative 1 minus 0, which is negative 1. So negative 1, 0, and 0, negative 1. And 0, negative 1. So I need a value of negative 1 over here. And it is going to be a straight line because it's t to the power of 1. And you can even check actually whether it's correct or wrong. The way is going to be very simple. Alright, so if you remember the equation of y equal mx plus c, so now the only difference is that y is being replaced by f of t, and I'm going to have x is replaced by t instead. So this is how my equation looks like. Alright, so here my gradient value is negative 1, and my intercept value is going to be 1. So c is equal negative 1, and m is going to equal negative 1 as well. And we know that when m is equal negative 1, my graph is going to be going down. So this is what happened over here. So this is what happened here. So when my value of t increase, so the graph is actually going down, and the intercept value is at negative of 1. So therefore, yes, we clarify that that's the correct line. And we're going to do the same on the other side as well, from 0 until 1. So I'm going to replace over here my value of t with 0 and 1. So when my value of t is equal 0, my function f of t is going to equal 1. and when my t value is going to equal 1, my function f of t is going to equal 0. So 0, 1, 1, 0. So 0, 1 is going to be somewhere up here, and 1, 0 is going to be down here, and then we are going to connect these two lines. So that is how it looks like. And straight away, like from this two, we can tell whether our function is going to be odd, even, or neither. So by now you should be able to identify the type of function already. That the fact that we have one function at the top, one function at the bottom, symmetric to each other. So this is a characteristic of being an odd function. Okay. And please do not leave your graph like this. So there's a hole from -3 until -1 and 1 until 3. So what you're going to do is you have to fill them in. Remember that the period value is equal to that everywhere there is 2 units distance on the graph, that is supposed to be a new cycle. Alright, so therefore for this case I'm going to have 3 cycles altogether. So what is the principal shape? The principal shape is going to look like this. For example, if I have a line that looks like that, my principal shape is that one line at the bottom and one line at the top. Okay, so therefore here I'm going to have one line at the bottom, one line at the top, another line at the bottom, and another line at the top. Okay, so that is how the periodic function looks like. Okay, so now that we are done with that, we're going to proceed with our calculation for B. We're going to find the Fourier series. And first of all, before we start with the calculation, so find the value of omega. So we know that t is going to equal 2. So omega, the formula is going to be 2 pi over t. So therefore, my omega value for this case is going to be pi. Alright, so now that we know that this is going to be an odd function, I did mention this to you before. So automatically our a0 and an, they are both going to be 0. You don't need to show this. So we know right away if it's an odd function, a0 and an is going to equal 0. So you don't need to calculate like what I did before in my previous example. So the reason I show you that before is because I want you to know why do they become 0. But now that you already know, no need for that. So straight away put that a0 and an is going to equal 0. Now all we have to do is just calculate for the third Fourier coefficient, which is bn. So this is going to be the formula for bn. We're going to have d plus t. So f of t sine of an omega t dt. So now let's do substitution. So I'm going to have 2 over 2, the integral. And remember, how do you find the d and d plus t? It is always from the function that give you out the shape. It's always from the lowest value of t and the highest value of t. And for this case, it's going to be -1 and also 1. So it's going to be -1 to 1 of the function f of t. So do not substitute the f of t yet. Sine of an omega t dt. Before you start substituting f of t, so please inspect the property first. So the fact that when we sketch f of t is odd, sine is also odd, and the product of these two is going to come out as an even function. I remember when we have an even function, we don't know how it exactly look like, but what we know about that is that it's going to be side by side and they're going to be symmetric. So instead of like integrating the whole thing, I can integrate only half of the area, which is going to be from 0 until 1, and multiply that by 2. So can you integrate from -1 to 0 as well? Yes. However, remember, we want to avoid negative numbers because it might make your calculation complicated. So that is why we pick 0 until 1 instead. Right, when I simplify it, become 2 over 2. And here, so my integration is going to be simplified to integration from 0 until 1. But now remember, this is only half of the area. When I wanted the whole, I have to multiply by 2. And now let's start substituting f of t. Alright, so f of t is going to be a function that covers from 0 until 1. And from the function given, which one covers from 0 until 1, it's going to be this function right here, which is 1 minus t. So therefore, I'm going to have 1 minus t. So multiplied by sine n, and we already know omega. Omega is equal pi. So I'm going to have sine of n pi t dt. Alright, the good news about Fourier series is that we are not actually testing your integration. Alright, so the only two possible integration is that one, direct integration, like what we did in the previous example, or two is going to be integration by parts that we have over here. So why is it integration by parts? Because if I have polynomial multiplied by a trigo, definitely going to be integration by parts. And you know that there are two ways of doing integration by parts, the formula and also the tabular method. I am always more comfortable with tabular method, so I'm going to use tabular throughout my whole example. But if you are more comfortable with the formula, then use the formula instead. It doesn't matter as long as you get the answer. So if you want to use tabula, so we always differentiate the polynomial, and there's no need to expand this, all right? No need to. It's just a waste of time. Put it together, 1 minus t, because both of them are polynomial. And we're going to integrate the trigger, which is going to be sine of n pi t. So when I differentiate this, I'll get -1 and I'll stop at 0. Integrating sine, it will be negative cos of n pi t over n pi. And when I integrate that again, I'll end up with negative sine of n pi t over n pi square. And I'll draw diagonal arrows. That's how it's going to look like this. And then I'm going to put plus and also minuses, and I'm done. Now let's put them together. Don't forget the 2 outside, so put it in. Include that in your calculation. And this negative over here, I'm going to multiply this by the whole function. And I'm going to have t minus 1. So that's what I'm going to do. I'm going to write this as t minus 1. So cos of n pi t over n pi. So that is my first term. And then I have negative, negative, and negative. So that is going to be negative of 1 multiplied sine n pi t and over n pi to the power of 2. And evaluate it from 0 until 1. So now I'm going to start substituting the lower and upper limit. So I'm going to start substituting t equal 1 minus when t is equal 0. And where are the t's that we're going to substitute? Right here. Let me highlight all the t's so it's very clear. So where are the substitution going to be done? Okay, first, let's substitute t equal 1. So when I substitute t equal 1 here, I'm going to have 1 minus 1. So that is going to be 0. So the first term is going to be 0. So the second term minus, I'm going to substitute right here equal 1. So I'll end up with sine of n pi. And underneath, I'm going to have n pi square. That will be the middle term. That is the case when t is equal 1. Okay, minus. And in the bracket over here, I'm going to put all the case when t is equal 0. So when t is equal 0, so here I'll end up with 0 minus 1. That is going to be negative cos of here. When t is equal 0, I'm going to have cos of 0. And that is going to be over n pi. And on this side, I'm going to have minus. So sine of 0 over n pi square. Okay. So that is how the substitution looks like for the case of t equal 0. So now I'm going to simplify this. All right. So sin n pi, so we have seen this before. So sin n pi is always going to be 0. And cos 0, that is going to be 1 using your calculator. And sin 0 is going to be 0. So now let's simplify this. I'm going to end up with only one term over here. So which is going to be very easy for us. So I'll end up with a 2. And that's going to be 0, and this is 0. And the only term I have over here is going to be negative and no negative. So I'll end up with a positive of 1 over n pi. So therefore here I get that my bn is going to equal 2 over n pi. Okay. And if you remember what I did previously, I had like for the previous example, so n is only going to be to have values for certain cases, and certain cases it's going to be 0. But for this case, it doesn't really matter. So there is always going to be a value for any term of n. So you doesn't have to replace whether it's going to be n even or n odd. You don't have to worry about that for this case, right? Because we don't have the -1 to the power of n term, and this is going to give a value every single time. Okay, so therefore there's no need for that. So for this case, so now I'm going to start writing my function f of t. So remember the formula for Fourier series, a half a naught plus sum from n equal 1 to infinity of a n cos of n omega t plus sum from n equal 1 to infinity of bn sine of n omega t. But again, for this case, a naught is equal 0, a n is going to equal 0. So we only have this term to substitute. So let's substitute right there. So I'll end up with sum from n equal 1 to infinity. So what is my bn? So that is 2 over n pi. And I'm going to have sine of n omega. So my omega is equal pi. So I'm going to have sine of n pi t. So that will be the outcome. Okay. So what is the difference between this and the previous one? So the previous one is because of this. Because there are certain cases, it's going to be when n is even and n is odd, that certain part is going to be 0, certain part is going to have value. So that is why we have to use this function right here. Okay, but for this particular example, there is no need to. Okay, for our recent case, not this one, where is it just now? Okay, so for this one, there's no need to, because this is not going to be 0 for any value of n. So you only do that when there are certain cases that it is going to be 0, but not for this one. So therefore, you can directly substitute that Bn is going to equal 2 over n pi. Or, like, instead of writing like this, I can also bring out the 2 and the pi, because they are not related to n. And I can write that this is going to be 2 over pi n, sum from n equal 1 to infinity, of sine of n pi t over n. So anyway, it's possible. You can leave it like this. So you can also bring out the 2 over pi, because they are not related to n. So either way, this is going to be our Fourier series for this particular example. So that's it.